Okay, so this is the name of the practice. It's called Practice Test 3 Solutions Double Single Replacement DOC. It's a Word file. And it's right at the top. Yeah. Is there an extra credit question on there? Yes, there is actually. The I think I left it on there. There's one to be on your test tomorrow. And it has to do with the well, let's see if it's on here. If it's not on here, I'll explain kind of what it is. Okay, so tomorrow I'm going to be giving you a solubility table, a common ion chart, periodic table, and a metal activity chart for doing single replacement reactions. Okay, the first questions are regarding just mixing up stuff to get solutions at different concentrations. And I need my okay. Now, and since tomorrow is a dry lab, I'm going to give everyone extra time as well. So you can have up to like 2 hours to do this thing if you need it. Okay, so how would you make 6 liters of 2.23 molar solution of C2H4O2, which is acetic acid, from dry ingredients? Okay, first thing we need to do is calculate the molar mass of the acetic acid. So we've got 2 C's, those are 12.01 a piece, so that's 2402. We have 4 H's at 101 a piece, so that's, and then 2 oxygens at 16 a piece. We have 06, 10. Okay, so that's the molar mass of acetic acid. Okay, so we need that'll give us the moles we need. And from the moles via the molar mass, we can get the grams we need. So we're looking at so 13.5 moles. Times the molar mass will give us grams. So this would be the directions. 810 dot because I need 3 sig figs, grams in 3 liters of water, mix, then bring the volume to 605 liters. Yeah,
That will be on the exam before we have to explain like that.
yes. I mean, this is a typical dry way to make solution up. You have dry ingredients. So I'm just going down the study guide, hitting all those. Okay, so any questions about that? Now you will see as I go this practice test, yeah. Mix, then bring the volume to 605.
Why do you put 3 liters?
It doesn't matter. It can be 2 liters, 3 less than 6.05. And the purpose of that is just to get it dissolved. Yeah, so her question is really a good one. I put down 3, but it doesn't matter what you put down as long as it's less than 6. You can put down 5.5 if you, I mean, it doesn't really matter. As long as it's less than the final volume. Okay. All right. Now the next one we're going to take and dilute a concentrated solution. Okay, we're going to make the same thing. I'm going to use 14.3 molar concentrated solution. So the calculations for this one is so the moles of the concentrated equals the moles of the dilute. What's different is the volume. So the first thing we're going to do is we're going to calculate the moles of the concentrated we need to get. Okay. Excuse me, we're going to calculate the volume of the concentrated. And then we're going to dilute that small concentrated volume out to the diluted volume. So we're going to solve for basically volume of the concentrated here. Okay, so we're looking at this is on the left is the concentrated side, so we're looking at 14.3 molar times the volume, which we don't know. And then on the dilute side, we're looking at 223 molar times 605 liters. Okay, and this comes from moles equals moles. What we don't know is the volume of the concentrated. So the volume of the concentrated is equal to 223 605 liters all over 14.3 molars. That cancels, leaves us with the concentration of the volume of the concentrated stuff. Okay, so we're going to take 0.94 liters of the concentrated stuff plus enough water to get it up to 605. So 605 minus the 94. We need the 511 liters of water to bring the total volume up to 605. This is the key on dilution problems. Because in dilution problems, you're always solving for the volume of the concentrated solution. Then you're going to dilute that down to the final volume of the diluted volume. Right. Top of this one up here. Now you can do the same thing when you're watching the video. Pause the video. Might be easier than, I don't know, 6-1 after another. Okay, all right, next one. What's the hydrogen ion concentration of the following acidic solution? Okay, we have 12 liters and 13 grams of hydrochloric acid. And remember, hydrochloric acid is a strong acid. So what we're going to do, we're going to get the concentration of this. And because that's a balanced equation, it's a 1 to 1 to 1. So once we know the concentration of HCl, we also know the concentration of the H plus and the Cl minus as well. Okay, so we have calculate the molar mass of HCl. H is 101. Chlorine is 35. Okay, so we've got 1345 grams. Now this is HCl now. And we've got and that'll give us moles of HCl, and that's all over 1234 liters. Now you can do this in 2 steps if you want, or you can do it in 1 step. First step would be to calculate the moles. You want to do it in 2 steps. Calculate the moles using that top numerator calculation. That'll give you moles. Then you're going to have moles over 12.34 liters. Or if you like math, you can go 1345 divided by 36 divided by 1234. That'll give you the same answer. Okay, so all of you that are uncomfortable with math, do it in 2 steps. It's much clearer what's going on, bless you, in 2 steps. Okay, so that's the concentration. Remember, square brackets is concentration. So that's the concentration of HCl, which is also equal to concentration of hydrogen ion. I guess it should be 4 sig figs, huh? Should be 4 sig figs, you guys, not 3. So it's going to be Okay, so you have to understand what a strong acid is. We're only working with strong acids in here, not weak ones. This problem would, if this was like acetic acid instead of hydrochloric acid, it should be like a 7 or 8 step a problem using the quadratic formula and all that stuff. So it's significantly more involved. Most of the acids of the world, however, are weak acids, but so the strong acids, and this is the most common one in Chem A, is hydrochloric acid. Occasionally we'll run across sulfuric acid, which is H2SO4, but I'll be using HCl 99.99% of the time, if not 100%, because it's easier than H2SO4. Okay, any questions about this guy? Okay,
So it's the same as the.
exactly. That's just via the balanced equation, stoichiometry. Yep, exactly. Because the coefficients are 1 to 1. Now, if this was sulfuric acid, then the coefficients would be 2 to 1. Because we have 2 hydrogens that come off, not 1. Okay, that's why I like HCl, because it's 1 to 1. Okay, picture taken. Okay. Okay, so what if we dump 2 solutions together? We've got one solution of sodium chloride and another solution, different concentration. We're dumping them together. What's the final concentration? Okay, so concentration is moles per liter. So we need to get the moles from each one, add the moles together, and then also add the volumes together. And that'll give our final moles per liter. Okay, so we're looking at this one first. So let's call this A. And this one B. So let's do A here. Okay, so we're looking at 156 moles per liter times 334 liters. That'll give us moles of A. Same thing with B. Okay, now we add them together because we're dumping them together. Okay, and we need to add up our volume. So we've got 334 liters. That's A. B is 136 liters. Gotta put the right numbers in with the decimal point. Okay, so we're looking at 1240 moles over 470 liters. So our new concentration is 264 moles per liter. Okay, but just keep in mind the focus of concentration, moles and liters. Moles and volume in liters. Okay. Everyone okay with that? All right, so we have a titration problem next. Titration is based on the neutralization. So we have moles acid equals moles base. At neutralization. And we're going to be doing, on the dry lab today, we're going to be doing about 4 of these, be more practice. Okay, so moles of acid, we don't know the concentration of the acid though. And by and large, acid-base titrations are done where you don't know the concentration of the acid. So you're titrating with a known base, usually sodium hydroxide, and a known volume of the base based on a burette reading. Okay, so we've got, now these milliliters have to be in liters because it's moles per liter. Now some people teach millimoles. And to me, if you've done a lot of this and you're in 1B, you can do millimoles. Up until you get to 1B, you'll be doing moles per liter. So if you have something given in milliliters, convert it to liters. So you're going to move the decimal point to the left 3 places. So we're looking at for the volume. And the concentration is okay. Moles of acid is, okay, we know 30 liters, 30 milliliters converted to, that's 3 sig fig, so we need another 0 there. And the concentration is, we don't know what it is, calculating it. So that means the concentration of the acid is equal to this guy on the right. All over now, if you can't convert the milliliters to liters in your head, do separate calculations. Get those over to liters. You want everything in liters. We're looking at 3 sig figs. So that's 285. And how do we know the reaction is at neutralization? How will we know that? Remember? we gotta have an indicator. And the indicator will tell us when that neutralization occurs. Because this is not valid unless the moles of base equals exactly the moles of acid. This calculation is based on that. So if it's not at that point, none of this works. So you have to have some way of figuring out when we're at neutralization. We can use a pH meter, we can use pH paper, or we could use a color-based indicator. The one we're using is called phenolphthalein. It's a very, very, very common acid-base indicator. It turns this nice, pretty pink. Ferguson's name of that is Barbie pink. I mean, it's really a cool color. I mean, it's just. Okay, any questions about that titration? And again, your dry lab is you're gonna be practicing your dry lab. Okay, describe a solution. Solution is based on two parts. And you can have one or more solutes, solutes, and one solvent only. And they are homogeneous. I mean, you cannot tell them apart. Think of vodka. Vodka is alcohol plus water. It looks like water, though. You cannot tell the ethanol from the water. Think of the air. You can't tell the nitrogen from the oxygen from the carbon dioxide. You can't tell them apart. So that's a solution, gaseous solution. In fact, that's one of the next questions is describe a solution that has more than two solutes. Well, air is a good example. Okay, the solvent would be nitrogen because that's the most. And then the solutes in the air would be carbon dioxide, oxygen, hopefully not carbon monoxide, but probably carbon monoxide. Okay, so that would be like air. And what's the difference between an acid and a base? Okay, acid. An acid dissociates an H plus. A base dissociates an OH minus. And that's from it's not zero, but it's a little above zero.
We need to know the pH numbers for being able to describe it.
You should know that, but it's not going to be on the test. Main thing is acids are less than 7, bases are more than 7, and neutral is 7. So 7 is the key. When you get into 1A or 2A, you'll be talking about the number 14. And that's related to the pH of the acid and the base. It's related to 14 based on water, because water is both an acid and a base at the same time. Okay, what's an acid-base indicator? What did we just talk about? That's when reaction is the acids equal base. And that's a neutralization reaction. Neutralization. Neutralization reaction reaches acid equals base. And that indicator could be a number of things, not just a chemical. It could be a meter. If you're in any kind of lab at all, you're gonna be using a pH meter, not an indicator. If we were in the 1930s, we'd be using an indicator. Even if you're in a professional CSI lab from the 30s, you'd be using an indicator. No instruments were available then, not very many anyway. Okay, all right, so that's solution questions. And you'll have one of each of these. Okay, balance and explain. Are there any questions about solution calculations or anything? Okay, all right. Balance and explain whether the following reaction, excuse me, the following equation will happen. Okay, is this a single or double replacement reaction? Single, because there's a metal there. If there's no metal, it's a double replacement. Okay, so if single replacement, that means something may or may not be oxidized. The aluminum may or may not be oxidized, and we need a activity chart to figure it out. So if the aluminum is above the lead, it'll happen. If the aluminum's below, so make sure I say that right. If the aluminum is above the lead, it happens. If it's below the lead, it won't. Okay, that's the only thing you have to remember. If the metal, the solid metal, you can also write that as Al0. Okay, so let's write the possible reaction. We have okay, so first of all, lead nitrate. Lead comes two ways. So which one is it? 2 or 4? How many nitrates are there? 2. And each nitrate is -1. So -1 plus -1 is -2. So that means that one lead is +2. So that's lead 2. Okay. Aluminum. Okay. We have aluminum nitrate. Now, is that the right formula for aluminum nitrate? Aluminum is Al plus 3. And nitrate, as we already mentioned, is -1 right over here. So how many nitrates we need to balance the aluminum? 3. And again, nitrates -1. Huh? Four. What do you mean? Three. Because they're -1 apiece, balanced against the aluminum, which is +3. That's why we need 3 nitrates, not 4. Better? Okay. All right. So now it's balanced. Yes, no. Okay, so we have a problem here, don't we? We have 2 nitrates and 3 nitrates on the other side. We need to balance this guy. So we have aluminums, leads, nitrates. On the left, we have 1, 1, 2. On the right, we have 1, 3, 1. It's those nitrates we have to worry about here now. What are we going to do?
So that
So we're gonna do like this. Like that. Now, there's no direct nomenclature questions. That comes into play when we're doing the balancing these single replacement and double replacement reactions. So you have to know that to answer, to balance these. Okay, any questions about how to balance that guy? Always, no exceptions, always check when you're done whether the equation is balanced or not. Like here, it wasn't balanced. The only thing that was balanced was charges on the names of the formula. But the equation itself was not balanced. There's two parts to that. Okay, so the next question is whether this reaction is going to happen or not. Is the aluminum above the lead? Well, let's go over here too. Okay, so here's aluminum. And where is lead? The aluminum's definitely above lead, so this reaction is going to happen. And why? Aluminum is above the lead. Okay. Next one. We have aluminum again, aluminum sulfate, which is that aluminum sulfate actually should be that. The sulfate's -2, aluminum's +3. We need to balance the charges. Okay, so is this reaction gonna, anything gonna happen? Okay, this is a double replacement reaction. So we have ions only, no metals involved. So the deal is we're gonna exchange the cations and see if there's a reaction gonna happen with that. So that means the potassium's going over the aluminum's going over the OH. So the question is, we have aluminum. We have aluminum hydroxide plus potassium sulfate. Okay, so aluminum's +3, hydroxide's -1. So we need 3 of these. Potassium's +1, sulfate's -2, so we need 2 of those. Now that's strictly from this here. And again, I'm going to be giving you all 3 of these for your tests. Periodic table, actually all 4 of these. Periodic table, the activity series, common ions, solubility chart. Okay, next question. Is this equation balanced? Well, first of all, let's figure out whether we're going to have a solid or not. So aluminum hydroxide, is that a solid Okay, so here's hydroxide. And aluminum is here. So it's black, so it's definitely a solid. And potassium sulfate is not a solid. It's white all the way across. So that's going to be AQ, aqueous. Does everyone understand the S versus the AQ? S for solid, AQ for dissolved, aqueous in water. Okay, next question. Is this thing balanced? Okay, well, let's see here. We have one aluminum, two aluminums, not balanced. So the aluminum, sulfates, potassium, and OHs. Okay, so we have two aluminums. Okay. We have one OH over here, 6 over here. Let's put a 6 there and make that a 6. Okay, what about potassiums? Okay, we've got 6 potassiums, 2 potassiums. So let's put a 3 here to make it 6 potassiums. What about sulfates? Well, we've got 3 over here, and we have 3 on the left. So now it's balanced. So this would be the molecular equation. Now, when you get to 1A, 3A, and possibly 2A, you know, another version of this is called the total ionic equation. And I don't cover that in this class. I get my opinions out of the scope of this class. But so there's really 3 equations. We're just leaving out the one, and that's the really gross detail on that one. It's easy to make mistakes because there's so little many details you have to worry about. Basically, what you do is you take everything apart. Instead of keeping them together, you take everything apart. It's a pain to balance and a bunch of stuff. Okay, so this is the molecular equation. Now, did anything happen? Did we form a solid? Yes or no? If we did form a solid, we have a net ionic equation. So to make the net ionic equation, we need aluminum, and we need hydroxides. So that's the net ionic equation. Do we have any spectator ions? We have potassiums and sulfates. They do nothing. They go through unchanged. And then here's another single replacement reaction. Okay, are there any questions about the double replacement? A lot of parts now. A lot of balancing equations, writing formulas, making sure the charge is balanced on the ions. Okay, we have one last question on this guy. It says balance and explain the following reaction. Okay, is this a single or double replacement reaction? Is there a metal present? Yes, so it's single. Okay, so let's write the possible equation here. So we've got so we're gonna the magnesium is going to be oxidized if this reaction goes. And if we look on our common ion chart, that's 2 plus 2. It's going to be balanced by the nitrate. -1 apiece. Plus aluminum, metal or solid. So is that gonna happen? So the question is the magnesium above the aluminum? Okay, here's aluminum again. Oops, wrong one. Okay, here's aluminum and here's magnesium above it. So is this reaction gonna happen?
No.
Correct, no. The aluminum has to be above the magnesium for it to happen. It's not. So this will be a no reaction. Let me correct myself, please. So the question is the magnesium above the aluminum? It is, so that reaction is going to happen. Somehow was mixed it up. All right, that's basically the practice test. You will see a test very similar to this tomorrow. Now, I'm going to have an extra credit on there, and it's going to involve taking an acid and a base, dumping them together, and see if one is it a neutralization reaction. It is because it's an acid and a base. That means the H's and the OH's are going to make water. They're going to go away. But if we have more of one than the other, we're going to end up with excess acid or excess base. And your job is going to be to find out the concentration of what's left over. And it's going to be very similar to this problem here. You're going to calculate the moles of H, moles of OH, which is more. You're going to find out, subtract the two, and then you're going to convert the moles of whatever's left over with the volume left over. That'll be the concentration. So it's very, very similar to this problem here. And again, I'm giving you lots of extra time. Now, this is probably going to be your most comprehensive test of the semester. This guy here. So don't, a lot of parts to this. But these are extremely important parts. Preparation for your next class. This is really, really important. There's stoichiometry here. There's solutions, there's acid-base reactions. There's nomenclature, notation, a lot of parts. And these are all weak spots of incoming 1A, 2A students. Big time. And this stuff is taught at like Davis. You're looking at 700 students in the class. So you don't get to ask questions, number one. When you go back to your lab, you get to ask the TA questions, assuming they speak English. Because all the TAs are brand new grad students. I mean, brand new. Their first year there. And if you come from another country, your English usually is not the greatest. I'm not judging, I'm just saying it's reality. So when I was there, if any of you plan to go to a big school like this, shop your labs. What I would do, in fact, all my friends would do this, we go from lab to lab to lab. We found a lab we liked, and we would kind of camp out there, and people drop big time. there. So we just wait for someone to drop, then we'd say, can we add? So, now I'm talking about anatomy, physiology classes, huge. Chem 1A classes, huge. Organic, freshman organic, huge. And what else? The biology ones, huge. Botany ones. I mean, these are like 500 to 700 in the class. It's unreal. It's so different than community colleges. So different. In fact, I'm going to a University of California Chancellor's retirement party in a couple of weeks. And I love to go to these things because these people haven't been in the classroom for years. I should say, most of them probably decades. And I'm always giving, and they love to talk to me because they want to find out what's going on with my students. And I tell them right out, I teach, a couple different schools, and one school I teach a prep class that they're trying to get rid of. They're trying to get rid of this class because it's wasting your time, quote unquote. And this is coming from the state legislature. I know. They don't know what they're talking about. And and they can't argue with me. I said, I see these students day to day. They're not gonna try to tell me that the research shows that students are wasting their time by taking prep classes. Because if you go into 1A without a prep, chances are you'll fail. And then you have to take the class over, so you're gonna be there an extra semester anyway. And your self-esteem is gonna be in the toilet, because you flunked the class. So which is better? My version's better. Prep class. And every community college is facing the same problems. Over at Sac City, we have Chem 300, which is the same as this class. Same deal, get rid of it. Because it's wasting students' time. They don't want students spending any more than 2 years on a community college. Nowadays, it's hard to get a degree in under 5 years. I mean, that's every school. Same thing. Anyway, I'm always talking about that. Okay, so any more questions about the tests tomorrow? Again, yeah.
I just have one about the last question you did. So it's not gonna happen because,
No, I made a mistake. It will happen.
okay.
Is that what your question was?
Yeah.
Yeah.
I also have a quick question about that last one. I noticed that we kind of finished without actually balancing out each individual.
We didn't balance it? Yes, we didn't balance it. Didn't I tell you to always check for balance? Well, let's balance it here. Ah. Okay, so we've got 1 and 1 for magnesium. Aluminum, 1 and 1. Nitrate, 3 and 2. So we have a problem. So let's kick this up to 2 and this up to 3. That gives us 6 and 6 nitrates. Aluminum is 2 and 2. Magnesium is 3 and 3. And yes, you always balance. Is this what you got? You're up here preaching, always balance, always balance. And what do I do? Not balance. Huh?
Just testing us.
Oh, yeah, right. I'm testing you. Yeah, right, you guys. I used to say all the time, this proves I'm human. I don't say that anymore. Now I say it proves I'm old. Okay, yeah, I'm glad you caught that because I want that way the video will be complete. Had I stopped it, the video would have been. Okay, that's it on this test. And again, The location of this practice test is Canvas files, test related, and do a search on the date, so the newest one will come up to the top. That's the easiest way to go. Okay. There are no more questions. We will end today.